Good morning. Hello. First of all, I very much like to thank Jan and Heather for inviting me to this wonderful conference. I really like this idea of the intersection of academia and practitioners, especially because I am, on one hand, I'm a professor at University of New South Wales, but I've also spent a significant fraction of the last 2 years as a software developer. So I'm kind of split personality. And for those of you who know me, you may expect me to talk about Haskell, but I have to disappoint you. No monads today. Let's talk about Swift. Swift is not just an interesting, clever language design, but it's especially interesting if you look at its ecosystem. In fact, there have been other hybrid object-oriented and functional programming languages, as you know, a few of them actually. But what's different in the case of Swift is not that it, as those other languages, nicely interoperates with the main language on the platforms it runs on and its libraries, but all these languages like Scala and F#, they are a minor player on the platform, whereas Swift is set to replace Objective-C. And that presents a unique opportunity, because why do languages become popular? We as language designers, we like to think it's the languages, but that's not true. It's the platforms. It's the proliferation of the platforms which make languages popular. And so Swift is going to dethrone Objective-C by decree, and it will become a mainstream language. That's at this point inevitable, as it will be the major language on the Apple platforms. And since there's a distribution for Linux now, and Apple has a very strong push into education. For example, in their last developer conference, they released a preview version of an iPad app, Swift Playgrounds, which is squarely aimed at the education space, in fact, at teaching kids to code in middle school and high school. It is set. The trajectory of Swift is set. So why is that interesting? Why should we care about this? Just another language which is going to get big. Well, it's interesting because the improvements of Swift over Objective-C are mostly to facilitate functional programming. In fact, type functional programming. So in summary, what we'll get is a language which encourages type functional programming in a mainstream language. I found that quite exciting when Apple announced the language 2 years ago at their developer conference, and I was in the process of writing, or I just actually started writing an IDE for Haskell supporting live programming using playgrounds, and I decided to jump in and to just write it in Swift. And it was one of the first Swift applications on the Mac App Store, I believe, and that's been very interesting. So let's get back to this. This is the core point. Swift encourages type functional programming in what will be a mainstream language, what arguably already is and will be one of the big languages. So types. Why are types important? Well, the conventional wisdom is types are there to catch bugs and prevent crashes. Or you could look at it from a different angle and say, well, you have to do less testing. You can get the same confidence in your code with fewer and simpler tests. Why is that? Well, if you look at your application, at the state space of your application, then there are some error states. Those are the states which lead to a crash or undecided behavior, and then we test for some of those. What the type system does it reduces the amounts of states the application can get into in the first place, which, yeah, it eliminates some bugs, but it also eliminates the need for some of the tests. But if that's the whole story, are types just an elaborate form of restraint for programmers? Something we shackle ourselves with to not fall across some obstacles? And what if that doesn't work? What if you're one of these people who says the type system really doesn't do anything for me because that's not the kind of bugs I'm making? I'm sure you've all heard this or said this yourself. Well, actually, the main thing about types is that they are a design tool. First and foremost, they are a design tool. They encode static. They are a language to talk about programs, specifically the static properties of a program, which is those properties which can be inferred and checked without actually running the program. But they are a guide. They help with code design, and then they automatically check the consistency of that design. So, in fact, actually, types are a design tool for language designers, and then the resulting language allows you to use it as a design tool for your programs. And that's the important thing. That's that's something the Swift team deeply understands. And one way to remind us of this is to follow this mantra often espoused by Yaron Minsky, to make undesirable states in your application unrepresentable. But let's get back to Swift. So Swift encourages type functional programming in a mainstream language. That's my main claim here. So let me, and if the type system is a design tool, then, well, let's talk about how we can use types to help us design programs. So I want to specifically focus on two particular features of Swift, namely value types and something called protocols with associated types. Sounds a bit scary. But to make this more concrete, I actually want to do this in the context of a concrete application, a little iPhone application. It's not very polished graphically. What the application does, it's a tracker for personal goals, like how often do you do this or that activity, which you really want to do more often, to keep track of that. And that application, it's got two modes. So on one hand, there's this overview mode, where you see your progress so far, and you can register that you did one of those activities you want to do. And then there's the editing mode, where you've got an overview of all the goals you've defined, and you can change them, and you can add or delete new goals and move them around. So that's a simple application. Let's have a look at how value types and these protocols help us to improve the design of this application, and in particular to use a functional programming approach. As we learned in the last talk, actually, I think functional programming is great in this context because of this focus of small narratives. Functional programming is all about local reasoning, very local and small. So, value types. What's a value type? Well, in Swift, there are two different kinds of value types. There are structs and there are enums. And you may think, well, you've got structs and enums in C. Well, that's how Swift, like typical Apple marketing, is very good at making things sound familiar. So they are non-scary. So they never talk about functional programming. They never use that term. They call things by familiar names and extend the functionality. So structs and enums in Swift, they are actually much more. So enums, as you can see in the second example, they're not just different alternatives, but each alternative can have values associated with those alternatives. And they can be parameterized. and they can be recursive, and there's pattern matching. So as a Haskell programmer, I actually call this an algebraic data type. But then everybody runs away, so Apple calls it structs and enums, and people are happy. But what's important about these value types is when we contrast them with reference types. So if I define a class ref point for reference point, and then I create an instance of that, so I get that, allocate it on the heap, and my variable points to it. If I assign it to a different variable, well, of course, I only copy the pointer, and then changing through this pointer, I, of course, affect what's accessible through the first variable as well. You all know that. The big difference with value types is if I do the same thing, then I get an instance, but once I assign it, well, I make a copy. And then changing that obviously does not change the value referred to by the first variable. So I get an immutable structure. Whether that structure is actually copied or not is irrelevant. The compiler tries to avoid copying, of course, but that's what's happening semantically. So that's great, because that gets us to our postmodern goal of small narratives, of local reasoning. It allows us to focus attention on a small piece of the code. We don't have to look at everything at once and consider impact of changes throughout the entire program. So I promised you to use these ideas in this iPhone application. We will do this by using something called an immutable model. So those of you who have written UI applications, probably most of you, those of you who have written Cocoa or Cocoa Touch applications will be very familiar with the model view controller pattern, which is the way to structure a Cocoa Touch application. Or maybe if you're living in Microsoft land, you're using the slightly more sophisticated model view model architecture. But in any case, you've got those model objects where the data of your application is stored and where you retrieve information for presentation. But these models, they're called model objects for a reason. They're objects with pointers to them. And when you pass them around, then you pass the pointers around, which means other objects, such as those controllers or views, often tend to accidentally change things in the model, or they change data in the model in an inconsistent manner. For example, because they're running on multiple threads, which is basically a necessity in modern mobile applications where you have to have a very fast responsive UI, so anything which could take a little longer has to go on a different thread. So using value types in Swift, we can avoid this problem. We just use a structure and enums to define the model. So in our concrete application, that would like this. We've got a struct, and it's got a few fields, and then one of these struct instances represents one particular goal. And to track the progress of goal, we pair it. This is Swift's notation for pairs or tuples, so in this case a pair, where you can use names to identify the different components of a tuple, to pair a goal with the progress you made towards the goal, and then we take an array of those to get the entire model state of the simple application. So by doing this, we can pass this around now, and we don't have to worry about any accidental changes because, well, it's a value type, it's not a reference type. So what we get, we avoid accidental changes to the model state, which gets rid of quite a few tests. And we make the whole thing much safer in the presence of concurrency, which, as I said, is really given in any modern mobile application. So that's number one. At this point, you may wonder, that's all great, but really, sometimes you want to change the model. How do you do that? That'll come later. You'll have to wait a moment, but I will tell you. All right, so number 2, we've used structs. Let's try to use enums. Well, as I explained, this application has 2 main modes. On one hand, there's the overview mode, and then we can also edit the set of goals. Now, in the edit screen, as it's quite common in these types of applications, there's a modal behavior. There's this edit, I don't know whether you can probably not read it on those screenshots, but on the top right corner there's a blue blob. It says edit. If you tap that on the left screen, you go to the right screen. And then you can delete goals, you can move them around, and so on. So this is a modal interface, quite common. And the trouble with it, with this type of setup, is that very often in the different modes, there's different types of state you want to keep track of, which typically means that you've got a few variables which may be nil or not, depending on in which mode you are. And whenever you transition from one mode to another, you have to make sure to change everything consistently. Otherwise, you get into this typical situation where your UI shows one thing, but you can't do the things you want to do, or there's an inconsistency in the state of the application. And that's quite common in this type of mobile UIs. So using enums, we can solve that by understanding that really what we're dealing with is just a state transition system, right? So there are various modal states the one screen can take, and we can draw nice diagrams with different states, arrows between them, and then we can define an enum for the different states. In this very simple application, it's just 2 different states. There's the display state and the editing state. And using those associated values, or as I would call them, arguments on a sum type, we can associate those parts of the states which are relevant for that particular mode with that state. Which means in the editing state, we always have active goals. In the display state, we cannot have them. There is not a null, an empty list, or a null pointer to a list of goals. They're just not accessible, and that's something the compiler can check. So when we use those, such an enum in this simple setup, we can extract the first line, extracts using a map function, extracts out of the array of goals the activity, whether a goal is active or not, and then wraps it into this editing case of the enum. And in Switch, we do pattern matching. In Swift, we do pattern matching using a Swift state, which is statement, which is a generalization of C-Swift, but it's really just like a case statement in Haskell, only with weird syntax, where we can pattern match on the component, extract the state components, but we can only get at the active goals if we are in the editing state. And it's something the compiler checks for us. So again, we lose some tests because there are a lot of inconsistent states which we cannot get into, which are not representable anymore. And moreover, the compiler can also check that our state transitions are exhaustive, as if in a switch statement we forget a few of those states. Well, that's hardly a problem in the simple application with 2 states, but once you get to something bigger, obviously that can happen more easily. The compiler will warn us about this oversight as well. All right, so this is how we can use value types, or immutable algebraic data types if you're a Haskell programmer or an ML programmer, how you can use them to improve the design and type safety of your application. All right, let's go on to something more sophisticated or complicated. Protocols. So if you're a Haskell programmer, then protocols are just type classes, and associated types are associated types. If you're a C++ programmer, well, it's a bit like templates with traits. Anyway, I earlier mentioned we kind of maneuvered ourselves into a corner. We made the model immutable. So now we can't accidentally change it. Well, actually, we can't change it, which is a problem because our user may want to change it. But what's mutation anyway? Let's look at a variable, a simple integer, which, when we initialize it, it's 25. Then we update it again, we update it once more, and then we update it to 42. This happens at different times, so one different way to look at this is to say, well, it's not just a mutating variable, this is a time series, right? It's one value strung out over time, or we could say it's a function over time to integers, or we could regard it as an unbound stream of values instead of something which mutates. Well, this is the idea behind a lot of these functional reactive programming libraries, or the way the Elm language operates. But the point is, what we can achieve with this setup is to make the flow of change in our code explicit. It's no longer a side effect through a pointer, but we can actually we actually have a handle at it, and we know where change happens, and which parts of the code are affected by a particular change. Moreover, a nice side effect when, well, a nice benefit is that once we regard change as a stream of values, well, it's a collection. And we can apply all our beloved collection operators like maps, filters, folds, and so forth, to make change propagation and manipulating changes even more compact and easier to understand. So how can we do this in Swift? Well, we could use one of these FRP libraries, which, okay, but actually this is a simple concept, and we can just implement it ourselves. So we start by this defining a protocol of observable values. Again, if you're familiar with Haskell, think type class. If you're familiar with Objective-C, think protocol. And but these protocols, they have an associated type. So the protocol we are defining is the class of types which can be observed. But that's not necessarily the same type as the values which we are observing. That is the observed value, which is implied by the type of observables. That difference will become clearer when we use that protocol, but it's important to keep in mind two different types in play here. And that protocol requires one function, or one method, if you like. And that's a method observe, which registers an observer, and an observer is just a function in this red box. It's a callback, if you like, which is being invoked every time and there's a new observation, or the value changes, the observed value changes. So based on this protocol, we have got two instances of that protocol. The first one is a stream of ephemeral changes, a parametric class called changing, of a particular parameterized by the type of values which we are observing. So the type of values in that stream would be int in our previous example with that mutating variable. So that class obviously implements the observe method, because otherwise it wouldn't be conforming to that protocol, but introduce one more method called announce, which we use to affect a change, or to announce the presence of a change in that value. So that's our replacement for an assignment, if you like. Now, that's one stream. In this case, when you register an observer, you will be notified of all the changes which happen after you've registered. But that's not always enough. So we've got a second form of observable values. You don't have to read all this code, which is maybe a bit confusing if you're not used to Swift's somewhat slightly verbose syntax. The important thing is that when we create one of these accumulating values, then we provide an accumulator function, the thing in red. The accumulator function's purpose is that given a stream of changes, the accumulator consumes those changes, maintaining some local state which is updated or accumulated every time we get a new change value, producing a stream of these accumulated values. And on registration of an observer, the observer is immediately notified of the current value of the accumulator. So these are the two forms of observables which we need in this little application. But based on this protocol, we can define a few collective operations. We can have a map function. Map on an observable passes in a function which is applied to every value in the stream and gives us a new stream. Merge takes two streams and merges them into one stream containing the changes in both of these original streams. The streams can have different types. And then finally an accumulate function which given a stream of changes produces one of these accumulating values which we saw on the previous slide. So now with that at our disposal, which is really just a few lines of Swift, we can implement the change propagation in the simple iPhone application. So we start by the model, which is this array of pairs of goals and progress counts. So the idea here in this table is G0, 1, and 2 are the goal structures, and the numbers to the right of them are the change counts, which are the progress we've made to achieving those particular goals. Now, we register two observers on that, one for each of the different modes of the application, the overview screen or the editing screen. And then both of these screens affect change, because in the overview screen, we can indicate that we've made progress towards a goal. Well, that's for the right column of the table. And then in the view on the lower part of the slide, the editing view, we can change goals. So that affects the left column in that table. So two different types of change, and we don't want, what we want to achieve here is that the screen, overview screen, can't accidentally modify the goals. And the goal editing screen can't accidentally modify our progress counts. So we achieve that by having two different sets of change information, which are then merged together. And these two different streams of changes, they're of different types. So the overview screen generates a stream of changes to progress, and the goal editing screen generates a stream of changes of edits to goals, different types. We can't mix them accidentally. They are merged by the merge combinator, and into a stream of overall edits, which we then accumulate to get the table as an accumulating observable value. So with this diagram translates very directly into the Swift code we are using to implement this, just putting the various functions at the arrows in this diagram together. And it makes it very explicit and checkable to the compiler how change propagates in this application. But the point I made in the beginning is this is not something which we've retrofitted. It is the manner in which we designed this application, which allows us to get that understanding as a human in the design process, but also allow the compiler to check the consistency of our design. So what we achieve by this setup is that parts of the views controller architecture of our application can't accidentally change those parts of the model they're not supposed to change. And we avoid conflicting state changes, for example, due to concurrent threads, which are sequentialized, for example, by this use of streams of changes. So to summarize, overall, please keep in mind, types are not a form of restraint to shackle you to your computer. First and foremost, they're a design tool. And Swift is itself designed with those ideas in mind to encourage typed functional programming, and those allow you to replace entire categories of tests. Thank you very much.
Hey there.
Hey.
So I come from the other side, from the Android world, and I just want to say that there's a very small few of us that are trying to apply the same approach into the Android world with the help of the reactive extensions in this case, so functional reactive programming. And I just wanted to say first as a comment, even though we don't have algebraic data types as a first class element in Java, they can be encoded, they can be created, because I've done it. I have a library that is called sealed unions that does exactly that for the JVM 8 and 7. So you don't need any kind of pattern matching, because you can do it with higher order functions using charge encoding. And my question is, um, the good part about the design is that when you're using it in your view model internally in memory, it works really great. But it kind of diffuses a little bit when you get into the edges, because the type system is not as powerful when you're going into the network, when you're sending information maybe in protocol buffers or any kind, or when you go into the databases, because they don't allow those types. How do you bridge that persistence that you're supposed to be having for the model in over time in those databases or in those network holes?
So that's so the point here was that in a typical application, the model information, of course, is not something which is just created in the application, stays there until the application dies, but you have to communicate over the network or make the data persistent by storing in database or something like that. So yes, so the interfaces are still the same. Um, for example, if you use something like core data on an iOS application to make your state persistent, then it's totally possible to wrap those mutable APIs in a way that you get an immutable view on them. And you mentioned React. I mean, React is doing exactly that, right? You've got the mutable DOM underneath in the browser, but the API which you present to the programmer, to the application programmer, is one of a function description and of functional updates. So basically, you can use those same techniques here, only that, well, either you've got a library or a framework which does that for you already, so some of those existing FRP systems try to do that for you, or it's something where you do the wrapping yourself. Then the person who you present this nicer interface is you in a different part of your application instead of some other person. But it's the same idea.
My question was a little bit more related about how do you express those types inside the database, not how you communicate with it, with those interfaces. What I mean is that you cannot store in a database an algebraic data type. You cannot store an either type. You cannot store a maybe, because the duality of them is not it's not easy to represent on a database or on a JSON schema, or the server has to know about it. So how do you approach those problems?
You have to serialize them. So of course you don't get the same expressiveness of types, say in an SQL database. So you serialize your model into something simpler, and which means that during deserialization from the database or from information which comes over the network, you will have dynamic checks.
Thank you.
Sure. So let me ask a question which I forgot to ask in the beginning. Who has used Swift at all? Who has used Swift in production? Okay. Try it. That's all right.
Okay. All right. Let's thank the speaker.